So in this video, I'm going to go over all the different kinds of NATs, or not all of them, many of the different kinds of NATs that exist. So it seems like a very simple abstraction of translating addresses from an internal to external interface. Well, it turns out there's all kinds of different ways you might implement that, and a lot of them are deployed out in the wild. And understanding these differences gives you a sense then of why NATs can be such a complicating factor when building applications. So recall, the model of a NAT is that, or generally the way it works, is that when there's some kind of communication from a node behind the NAT to an external node on the internet, the NAT sets up an internal mapping between a mapping internally to it in its memory between an internal IP address and associated port to an external IP address and port. And so when this server A tries to open a connection to the web server on S at 18.181.0.31, so it's going to port 80 on this host, and it's coming from port 45.1.2, the NAT rewrites all of those packets, including TCP SYN and then all the data packets, to be coming from its own IP address and port 6641. That's what the server sees, and then when the server sends messages back, the NAT translates them back to port 45.1.2. So that's the simple model. And there are two basic questions that come up. First is, what packets does a NAT allow to traverse these mappings? The second is, how and when does a NAT assign these mappings? When does it create them? So I said when you generate packets, but turns out it can be a little more complicated than that. Like, when does it tear down those mappings? It doesn't keep the mapping forever. So it turns out there's a nice RFC that sort of goes through the classifications and terminology I'm going to use in the rest of this video, 3489. So if you want to read a little bit more about some details and really the precise way these are laid out, take a look at RFC 3489. So the first kind of NAT is what's called a full cone NAT. And this in some ways is the one that plays the nicest. And a full cone NAT is called that because it is the least restrictive in terms of what packets it allows to traverse a mapping. In that way, it's a full cone, and the things which are allowed in are large. And so the basic model of a full cone NAT is that any packet that, say, this is for the particular, say, protocol TCP, any TCP packet that comes into the NAT to this IP address port pair will be translated to this IP address, this port pair, regardless of what the source address and source port are. This is the least restrictive. So if I have some other server, say S2, that has some IP address A, and it's sending a packet from port A prime, and that packet with source port A prime is sent to 128.34.22.8 port 6641, the NAT will translate it, and my server, my host here, will see something coming from A prime arriving at port 10.0.0.101, port 4512. Now, it might discard that packet, it might send an ICMP error, but the point is the NAT will do the translation. It's the least restrictive. It's a full cone. So in addition to full cone NATs, there are also restricted cone NATs. And what a restricted cone NAT does is it filters based on the source IP address. So in a restricted cone NAT, the NAT will translate packets that come from the same source address as is intended on the external mapping. So when the NAT sets up the mapping between the internal address and port pair and the external address and port pair, it includes the address of the other endpoint. And so in this case, if I have S2, which tries to send a packet from A prime, address A prime, the NAT will not allow that packet to traverse. It'll discard that. It'll either send an ICMP error or it generally will not translate that packet, and host A will never see it. However, if server S were to send a packet from IP address S, and then let's just say port 10,099, that will be able to traverse the mapping in the sense of it's coming from 18.181.0.31, and so host A will see a packet from 18.181.0.31 port 1099. And it'll come in destined to 10.0.0.101 port 4512. So that's a restricted cone NAT. It will filter based on the IP address but not the port. So the last kind of a NAT, or of these three major classifications, is a port-restricted NAT, where it behaves like a restricted cone, except it also filters on port. So in this case, when a packet comes in from some external host to 128.34.22.8.6641, the NAT is storing also what the expected IP address and port are. And so in this case, if I have some server S2 that tries to send something from A prime, the NAT will not translate that. That's seen as an error, an ICMP, etc. No route to host, whatever error it thinks is correct to specify, depending on the conditions. But similarly, if server S tries to send a message from port 1099, that will not traverse either, because it doesn't match the port in the mapping. So only packets from this IP address port pair, 18.181.031, port 80, will be allowed to translate to 10.0.0.1.45.12. So only this particular pair can traverse the mapping. So the last and the final kind of NAT is something called a symmetric NAT. And what makes a symmetric NAT different is not only is that, first of all, it's sort of by definition port restricted, but there's the fact that packets coming from the same source address and port internal to the NAT that are going to different destination addresses and ports are given different external address port mappings. So if you look at this figure, you'll see what I'm saying. So here I have host A, and it's sending packets from 10.0.0.101, port 4512, right? And first it's sending them to 18.181.0.31, port 3311. So the NAT sets up a mapping. And the mapping between this internal address port pair and this internal address port pair is 128.34.22.8.6641. And so packets that A sends to port 3311 on this IP address will be translated to have this IP address and this port. However, if A sends packets to a different external IP address and port, like let's say even the same port and the IP address differs in 1 bit, so it's also sending packets to S prime of 18.181.0.32, port 3311, the NAT sets up a completely different mapping. So even though this port address pair is the same for both of these streams of packets, the fact that the destination port address pair is different means the NAT sets up a separate mapping. Port 6641 and port 9821. So different destinations receive different mappings. So it turns out that, and this is just to give you one concrete example of ways in which NATs can really disrupt applications. So let's pretend that host A is sending UDP traffic. And this UDP traffic is for a massively multiplayer online game. So this is a true story. There's a friend of mine who was working on the servers for this when this happened. It's back in the late 90s, and he made an angry call to the Linux NAT developers. And so the issue is that this massively multiplayer game runs on many servers, and there's times when somebody runs from one island to another or wherever, and they need to change which server they're on. And so what the system would do is it would tell the client, oh, okay, hey, you've been talking to server 18.181.0.31. You should start talking to server S prime at 18.181.0.32 on this port, even the same port, doesn't matter. Like here, say port 3311, and both of them you want to talk port 3311. So hey, please start talking on this other to this other host. And the issue is that the NAT, this symmetric NAT, would create a new mapping. And so S was seeing the client covering from port 6641, but now suddenly the client is covering from port 9821. And there was no way for the system back here to know that, because the NAT just sets this up and it can arbitrarily decide, so the connection would break. So the observed behavior was that because there was a symmetric NAT, that whenever someone would try to migrate from one server to another, they would disconnect. So here's an example of by adding this smarts into the network, suddenly you're seeing a behavior different from the simple strong end-to-end argument, and there's this added behavior which is really hard to manage and really hard to take into consideration, because there's no way really for S prime to know the port 9821 is the port that A is going to start communicating on. So this is just the most basic overview of some ways in which NATs can differ in their behavior. It turns out that there's many more complications, all kinds of different things NATs could do. And that RFC I mentioned earlier, in fact, goes through all of the really diverse behaviors you saw when NATs first became popular, before there was really standardization of what should happen. There's all kinds of things like static mappings. You can tell the NAT, hey, just set up this static mapping between the external host IP port pair, my external IP address and port, then to an internal one. This is, say, if you have a web server behind your NAT, you can tell it, hey, anything that comes to port 80, forward to this server on port 80. You have things like triggers. If you see packets going out in one direction, then also set up this additional mapping. This is really useful in some of the early days of first-person shooters, online games, where, again, they hadn't been built with NATs in mind. There's really diverse NAT behavior. There's all kinds of more complex things that happen. But so it turns out, because of all of the headaches and messes that NATs started creating applications, the IETF went and came up with a bunch of recommendations as to how NATs should behave. So the general behavioral recommendations specified in RFC 5382 for TCP and 4787 for UDP. So just to give you one example of kind of some of the weird edge cases that a NAT can consider and some of the things that are specified here, I'm going to talk about hairpinning, which is this process of what happens when you have a node that's behind your NAT and it sends a packet to one of the external interface port pairs that the NAT has, one of its mappings. So basically, I have a node that's behind the NAT and is trying to traverse one of the NAT's mappings. So here's the example. I have this NAT 128.34.22.8. And I have hosts A and B that are behind the NAT, and they're both connected to a switch. All right, so A has has address 10.0.0.101, B has 10.0.0.99. And let's say we're doing some kind of IP telephony, which is coming from port. This is a UDP traffic, so it's port 4512 on host A. So it's using port 4512, and this is translated to port 6641 on the NAT. So the question is, what happens when B tries to send traffic to 128.34.22.8 port 6641? Basic question is, so the NAT is going to arrive at the NAT, and the NAT is going to translate it. It's going to translate this, assuming that it is a full cone NAT. It's going to translate this to 10.0.101 port 4512. One question you can ask is that, well, it's going to translate the destination IP address and port. What should it do to the source IP address and port? Should it translate that as well? That is, should this packet arrive at A seemingly coming from 128.34.22.8? Or should this packet arrive at A coming from 10.0.0.99? Well, so let's walk through what happens if the NAT doesn't translate the source address and port. So this packet will go through the switch, it'll go to the NAT will rewrite it to be going to 10.0.101.4512, and so what A will see is a packet with source 10.0.0.99, let's just say port X, doesn't really matter, destination 10.0.0.101, port 4512. And let's say it likes this packet, it wants to respond, and it sends a response. That packet is never going to reach the NAT. It's going to possibly just go directly through the switch. And because it doesn't go through the NAT, it's not going to be translated. So B is going to send a packet to 128.34.22.8 port 6641, and we'll see in response a packet from 10.0.0.101 4512. So this breaks. This is not what you want to do. Instead, when this packet goes up to the NAT needs to translate it. So it comes in as a packet from, so source 10.0.0.99 port X, destination 128.34.22.8 6641 needs to be rewritten to be source 128.34.22.8 with some port, let's just call it X prime, destination 10.0.0.101 port 4512. And by so doing, then, because now the source is coming from the NAT, when A sends a response, it'll go back up to the NAT, where the NAT can retranslate it and forward it back to B. So it's called hairpinning through the model because you have to actually go back through this device, sort of like a hairpin. It comes back from telephony networks, is the terminology. And so here's this example of a very specific behavior that a NAT has to have. And if it doesn't, then in this little edge case where B ends up sending a packet to A based on an external mapping, if you don't do this, it will break. So this is just one of the many tricky edge cases that NATs introduce and which are specified in these RFCs.